In today's lesson, we are going to be looking at tree diagrams and organized counting. So tree diagrams display all the possible outcomes of an event. Each branch in a tree diagram represents a possible outcome. So tree diagrams can be used to find the number of possible outcomes and calculate the probability of those possible outcomes. So for example, we see here we have a coin. Basically, it's two flips of a coin. Right? Our first flip, we could have either heads or tails. It's a 50-50 chance. And then our second flip, depending on what we got. So if I got a head the first flip, I could get a head or a tail in the next flip. If I got a tail in the first flip, I could get a head or tail in the second flip. And I can list all my possible outcomes. Right? And when we read our possible outcomes, we're looking at the entire pathway of a branch. Right? So this one would be head and head. That's one of the outcomes. Head and tail, the entire pathway, that's another outcome. Tail and head, tail, and so on. So it's just a visual way where we can see the different outcomes and count how many different possible outcomes there are. So for example, when buying a car, you have the following options: cloth or leather seats, two-door or four-door, and red, black, white, or silver paint. We want to draw a tree diagram to illustrate the number of choices we have when buying the car and how many possible choices do we have. So I'm always start off with our first decision. So our first one is going to be the seats. We can have either cloth or leather. Depending on that, we make another decision. So our next decision is the number of doors. And there's only two options. Right? It's either a two-door or a four-door. And the same options would be for leather. You have a two-door or a four-door. And then lastly, actually, let me do those in a different color just so we don't get them confused. So we have our seats, then we have our door, and our last one is going to be the color. Now, this one might get a little bit messy. I'm going to give myself a little bit more space here. Because for each one, there's going to be 1, 2, 3, 4. Right? Red, black, white, or silver. Let me adjust that a bit. Red, black, white, silver. Same thing for four-door. 1, 2, 3, 4. Red, black, white, silver. Same thing for two doors for the leather. Let me just move this down a bit. Give it a bit more space. 1, 2, 3, 4. Red, black, white, silver. And then four-door, red, black, white, silver. Thankfully, we don't have any other decisions to make after that, because then I don't think I would have enough space for my tree diagram. But to figure out the number of choices that we had, we could go through and count every single pathway. Or an easy way to do it is just to count the last. How many letters do we have in the very last row of choices? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 possible choices. If I wanted to, I could go back and list all of them. Right, like you have cloth, two-door, and then red. Then you'd have cloth, two-door, black, cloth, two-door, white, cloth, two-door, silver, cloth, four-door, red, and so on, so on, so on. Right, but if I'm just figuring out number of options, I can just count the last row, and then if I had to, I could go back and look at what are the different pathways or what are the different outcomes. Next example, you have a three question true or false quiz and have no idea what is going on in class. If you completely guess on each question, create a tree diagram for the possible combination of guesses you could make. So I'm going to make my first question. So for the first question, I could guess either true or false. Second question, Let me give myself a little bit more space here. So the second question could also be true or false. I do that for, if I answered false the first time, it could answer true or false for the second, and then branch it off again for the third question. True or false, true or false, true or false, true or false. And so those are all the different combinations. So I could go through and say my combination or my possible guesses are true, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true. And let me just move this up just to make it nice and neat in just one row. And the very last one, false, false, false. You don't have to write those out. You could just look through each pathway if you had to. And if we wanted to count again, we could go through and just count the very last one, number or letter in each row. We have 2, 4, 6, 8. 8 possible combinations of answers. So 8 possible combinations. These are all the different pathways. But again, if it's just asking for the tree diagram and the number of possible combinations, you don't need to list out every single one. Determine the probability or the possibility of guessing false 3 times. So if we want to guess false 3 times, there's one way that could happen, right? This is the one scenario out of 8 possible ways. So the probability of guessing false 3 times is 1 out of 8. Or I believe it's 0.125 or 12.5%. Guessing 2 trues and 1 false. So 2 trues and 1 false. So if I look at them, I have this option, this option, this option. So I have 3 options, right? So sometimes listing out all the possibilities or different combinations is helpful because it's easier to read rather than having to go through and look back. But it's dependent on what you find easier. So 2 trues and 1 false, we see that there are 3 out of 8 options. That doesn't reduce any further, but that works out to 0.375 or 37.5%. So there's a 37.5% chance of you guessing 2 trues and 1 false. B, or I guess number 3, passing the test if all the answers are true. So if all the answers are true, that means we have to get 2 trues and 1 false, or 3 trues. Right, so we could get perfect, or we could get 2 right and 1 wrong. We can't get 1 right and 2 wrong because that would be 1 out of 3, which would be considered a failing mark. So if I look at all these options, I know from the last one, 2 trues and 1 false. There were 3 options. That's from the last question we just did. And 3 trues, if I go back up, 3 trues, there's only the 1 case. So there's only 1 option. So the probability of passing is going to be 3 plus 1, or 4 options out of 8, or 0.5, or 50%. So if I put all the answers, or if all the answers on that quiz or test for those true and false were all true, you'd have a 50% chance of passing if you guessed. Last example, suppose a couple would like to have 3 kids. Determine how many possibilities there are. So very similar to the last one. First child, boy, girl. Off of each child, boy, girl for the next one. And for the last one, so tree diagrams can get a little messy. depending on how much space we have. So try your best to at least to have them spread out. So we want to determine how many possibilities there are. Again, we can go through and list or count the last or the number of letters in the last spot. In this case, there are 8 possible outcomes. If I wanted to list them all, because it does look like I have questions coming up, so it might be easier if I do list them all. So they could have all 3 boys, boy, boy, girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl. Let me just bring this up a little bit. Girl, girl, boy, girl, girl, girl. So those are 8 possible outcomes. What's the theoretical probability of at least one girl? So at least one girl means 1 girl, 2 girls, or 3 girls. So probability of at least 1 girl, we know it's going to be something over 8 because there's only 8 total possible outcomes. So you could look and say, okay, well, how many options are there where there's at least 1 girl? Or you could think of the opposite. What's the opposite of at least 1 girl? Opposite of at least 1 girl is no girls. So you could think, okay, well, if there's 8 possible ways, there's only 1 way where there's no girls, right? Where it's all 3 boys. So that means everything left over has to be at least 1. It's a bit of a trickier way to think about it. So what you could do is just go back and count and how many options are there where there's at least 1 G in my list of 3 letters. So it'd be the 1, 2, 3, 4, 5, 6, 7. So there's 7 ways out of the 8. The only way that doesn't have at least 1 girl would be the one case where we have all 3 boys. So 7 out of 8. That doesn't reduce, but 0.875 or 87.5% chance of having at least 1 girl if they have 3 kids. What is the probability of at least 3 girls? So at least 3 girls mean 3 girls or more, but because we only have 3 kids, we only look at one case where there's 3 girls. That case only occurs once out of 8, or 0.125, or 12.5%. So that's the probability of at least 3 girls. D is saying, suppose the couple wants to have a boy first and then a girl second. What is the probability or the likelihood of that happening? So if I go back and look at my scenarios, the probability of a boy first and a girl second. So that's only the one pathway going up. It has to be boy, then girl. And it doesn't matter what the third one is. It doesn't say it, so we can assume that either option is fine. So that's really only boy, girl, boy, or boy, girl, girl. So there are only 2 ways that this could happen. So 2 out of 8. That does reduce to 1 over 4, or 0.25, or 25%. So there's a 25% chance of having a boy first and a girl second. Now, the next thing we're going to be looking at is organized counting. And organized counting is a fast way to figure out the number of possible outcomes without having to do a tree diagram, right? So some of you may not have liked drawing the tree diagrams that we did earlier. It can get crowded, it can get messy, and I understand that. So if the situation only asks for how many possible outcomes there are, and they don't care about what the actual outcomes are, like we don't care if it's like true, 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 or true, false, true, whatever the case may be. We just want to know how many options there are. We can use organized counting. And organized counting follows the principle that the word and means to multiply. So if we're making choices and it's one choice and another, then that will signify that we have to multiply, right? So if we think answering the 3 questions, you answer the first question and the second and the third. So and in there is implied, and it's going to multiply. So if there are m ways, m just represents an unknown number. If there are m ways to do the first event and n ways to do the second event, then the total number of ways the two events can be formed is going to be m times n. So we're just going to multiply those two options, or those two numbers together, and that will tell us the total number of ways that those two events can happen. Now, we can have more than two events. We just multiply it by a third value, or 4 events, we multiply it by 4, and so on. So let's go back and look at each of the scenarios that we just looked at, and just look at the different number of possible outcomes. Right, so if I look at the first one, buying a car, you have the following options: cloth or leather, 2-door or 4-door, black, and then the choice of paint. We want to figure out how many options there are, or how many total choices there are. So for the seats, there are 2 options. For the doors, there are also 2 options. And for the paint, there are 4 options. Now you can think about it. When you're choosing or buying the car in this scenario, are you choosing seats or doors or paint, or are you allowed to have all of them? Right? You're not going to go into a dealership and like, yes, I would like a leather or a car with leather seats and a 2-door car with leather seats, and you'll be like, no, sorry, you can only choose one or the other. You can only choose the number of doors, and then have no seats, or choose seats but none of the door options, right? Which isn't really the case. You're allowed to choose or have multiple of them, or each option is allowed to occur at the same time. So we are going to be multiplying. So all we have to do is just say, okay, well, 2 options for the seats, or multiply 2 options for the door and 4 options for the paint. So 2 times 2 times 4, we get 8 times 4, 4 times 4, which is 16 possible choices. And if I go back up and look at that scenario, there are 16 possible choices for that one. And I verified that with the tree diagram. Now, the only situation is for this one, it doesn't show us what the actual outcomes are, but maybe we don't care. We just want to know how many different ways how many different ways or different choices could we have. Number 5. So again, going to the true or false question, right? We want to completely guess. Technically, it should be how many ways. How many ways could you guess? So again, let's think about it. My first event is the first question. And then you have 2 options. Right? You have true or false. Your second question, 2 options again, true or false. And your third question, again, you have 2 options. Now, with these questions, or with the true and false questions, you're not answering the first or the second or the third. You're answering all 3. So you're answering the first and the second and the third. So we can say 2 options for the first event times 2 options for the second times 2 options for the third. 2 times 2 times 2 is 8. So there are 8 possible combinations. And you could go back and look at that scenario. You could look at that question or that tree diagram if we scroll back, right? 8 possible combinations for answering the 3 true and false questions. And the last one, couple having 3 kids, right? How many possibilities are out there? So the first child, there are 2 options. Second child, 2 options. Third child, 2 options. So very similar to the last one, we can just do 2 times 2 times 2, which is 8 possibilities. And if we go back and look at the tree diagram for that one, we see that there are 8 possible outcomes as well. Right. So the organized counting is a nice way where we can just quickly multiply numbers to see how many possible options there are without having to worry about drawing a tree diagram. Now, the only downside is we don't get to see the actual different outcomes. But again, sometimes that may not be the case. That may not be a concern. We're more concerned about just the different number of possible outcomes and not what they are. So if that is the case, then we do have an easier way to determine that. But if we do need to know the different ways, maybe for a probability question, then we might have to do the tree diagram still.